Hey class, we're going to do 3.3, which is on the addition rule. So we had the multiplication rule, which was for AND probabilities. The addition rule is for OR probabilities. So the first thing we'll need is what's called mutually exclusive. And that just means two events cannot occur at the same time. So I kind of think of it as a Venn diagram where if there are no intersection, it's mutually exclusive. If there is an intersection, it's not mutually exclusive. Some examples of that. Let's suppose we roll a six-sided die. Event A is rolling a 3, event B is rolling a 4. And notice there's no possible way that that could happen on the same roll. So that would be what's called mutually exclusive. Mutually exclusive. Let's just do that. Whereas in the other example, event A is the student is male, and the event B is the student is a nursing major. That could happen with the same selection if the student is a male nursing major. So this would be not mutually exclusive. Okay. And then we have some formulas. So there's our main formula here. Basically what you're going to be doing is adding the two probabilities together. So OR kind of translates to addition in probability. But you have that last piece, you have to subtract off the probability of A and B. That's basically you're subtracting off this overlap. If you think of that at those intersections. If there is no overlap, meaning they are mutually exclusive, notice that piece just drops away because there's no overlap. So it's a little bit easier. Okay, let's give it a go. So you randomly select a card from a deck, find the probability that you get a 7 or an ace. So there's the keyword OR. That means I'm probably going to be doing some adding. So if I did my notation, probability of 7 or ace, right, the formula is probability of 7 plus probability of ace. And then do I need that last piece? Well, I don't need it because there's no possible way that you can get a 7 and an ace, right? A 7 and an ace are mutually exclusive. There's no card that's both a 7 and an ace. So I could stop right there. I just need to add the individual probabilities. Okay, so probability of 7 is 4 out of 52. Probability of ace is 4 out of 52. And then I'm adding with a common denominator, so that's 8 out of 52. And notice you probably could have jumped right to 8 out of 52 because there's 8 cards, 4 7s, 4 aces out of the 52. But this is demoing how you can use the addition rule, which will help in future problems. All right, reduce, done. Okay, now part B is an example where we have not mutually exclusive events. Probability of an ace or a club. So the way I'm going to work this one out, probability of ace or club, I'll just do C for club. That's probability of ace plus the probability of club, but then I have to subtract off any card that's both ace and a club. Right, going right with that formula out above. So probability of ace, 4 out of 52. Probability of a club, remember the suits, there's 13 of them, 13 out of 52. And then now, the reason I'm subtracting, basically I'm subtracting off any double counts, any overlaps, right? Because I added aces and clubs, but remember, there is a card that's both an ace and a club. You can look back on that graphic with the cards. Right? There's one ace of clubs. I've double counted that card, so I got to subtract it off. Right? I only want to count one of them, not two of them. And then, so there we got it, 16 out of 52, which reduces to 4 out of 13, and we're good. Okay, here's another example. You roll a single 20-sided die. Whoa, that's a lot of sides. Find the probability of rolling a number less than 8 or rolling an odd number. All right, so probability of less than 8 or odd. Okay, I gotta do probability of less than 8 plus, because it's or odd. But it is possible to get less than 8 and odd, so I have to subtract those off. Okay, probability of less than 8. How many numbers are less than 8? There's 7 of them, right? 1, 2, 3, 4, 5, 6, 7, not including 8. So that's 7 out of the 20. How many odd? 1, 3, 5, 7, 9, 11. Okay, well, I think there's 10 of them altogether, right? Odd numbers, half of the numbers are odd from 1 to 20. Okay, and then what do we double count? We double counted any number that's both less than 8 and odd. Right? That would be the 1, the 3, the 5, and the 7. That's 4 of them. So subtract those off. Okay, just subtracting off the double count. 13 out of 20, that doesn't reduce, and we're good. Okay, so basically the formula is pretty easy to use. Just if there's overlap, we have to subtract that double count. If there's no overlap, just add the probabilities and you're good to go. Okay, we have one more page, maybe with some empirical data. So here's a bar chart showing the ages of respondents. Okay, so find the probability of anyone in their 30s or 40s. So or just means add them up, right? 30s or 40s are here and here. So I could just add those up and I'm good to go. So not too bad, right? That's going to be 28. And does that say 57? Okay. Now notice I also have to divide by the total for the probability, right? So the sum of all of these numbers, if I add them all up, that equals 230. So that's the sum of the frequencies, right? So I got to divide by 230. And notice with addition, you can divide each number by 230, but when you're getting a common denominator, you're putting them all together anyway. So you could just write this, right? That's the same as writing 230 under each individual number. Common denominator, you're going to put them together anyway. So this is 85 over 230, and this one wanted a decimal, 0.370. How about older than 49? Okay. Older than 49 would be these guys, right? So we have 89 and 37. Also, one note, notice we're working with mutually exclusive events, okay? Because you can't be 50 to 59 and 60 over 60. So there's no overlap in these bars. So that's why we're not subtracting anything off. 548. My calculator. Okay. All right. How's that look? Looks pretty good. Okay, let's try one more example. We got one with, again, one of these two-way tables. All right, we got blood type, positive, negative. Okay. Randomly selected donor, probability that the type O or type A. So type O or type A, mutually exclusive. Yeah, there's nobody that's both O and A. Right, there's no overlap in the columns O and A. Here they are. There's the O and the A column. Either you're in the O column or the A column, you're not in both. So I could just add them together, right? There's all the type O's, there's all the type A's. 184 plus 164, and then common denominator will be that 409. Right, so we got 348 divided by 409, and we got a final answer of 0.851 on that. Okay, so there's a mutually exclusive example. How about the next one? B or negative. Now we've got some overlap, right? Because our B's are here, our negatives are here. Here's some overlap. There are 8 people that are both type B and negative. So when we're calculating this one, or I could still just start doing the type B. So type B, there are 45. Negative 65. Those are coming from here and here. 45 plus 65. But 8 of those, 8 people in those two lists are in both of those lists. What did I say? So there's 8 people that are both type B and negative. So I just double counted the 8. So I've got to subtract it off. Right, and then divide by my common denominator, 409. And so this is going to be 369 out of 409, which is 0.902. Let's try one more of those. All right, let's clear all the highlights. Okay, A, type A, grand total, 164. Negative, positive, right there. Right, grand total, 344. So I'm going to add those together. 164 plus 344. But again, I've double counted. There are, if I look at the intersection there, 139 people that were just in both of those totals. So subtract it off so they don't double count them. Divide by the 409. Do the math, and we're good. I totally messed this up. This is the 369 out of 409. You probably were like, what is he doing? Yep, that's there. Right? I just, my eyes glanced down to the wrong thing on my notes. So that one's correct. This is the 0.902. Make mistakes sometimes. It's all right. Go back and fix it. Back up here. Obviously, I wasn't paying attention because there's no way that's even near 369 on that one. Good thing this thing erases. Okay. 45 plus 65 minus 8 is 102, right? So this one is 0.249. There we go. I fixed it. You were probably thinking, oh man, he's not going to fix that. It's not a good video, but I did it. I fixed it. It's all accurate. Hopefully those make sense. So in summary, when you're doing OR probabilities, add the two together, and then you may or may not need to subtract. If there's overlap, you got to subtract off that double count. No overlap, just straight add, and you're good. Okay, so we're done with 3.3. We're moving right along. So I'll see you in the next video for 3.4. Hope all's well. Talk to you later.